Inorganic chemistry is the branch of chemistry that studies compounds that do not contain carbon-hydrogen bonds. Inorganic compounds can be classified into four main types, such as acids, bases, salts, and oxides. Let's explain acids first. Acids are substances that produce hydrogen ions when dissolved in water. They are known for their sour taste. Acids have the ability to turn blue litmus paper red, and acids often react with metals to produce hydrogen gas. Acids are further classified as strong or weak acids. A strong acid is an acid that completely dissociates into its ions in water, releasing all of its hydrogen ions. This means it ionizes 100%. Some common examples of strong acids are hydrochloric acid, sulfuric acid, and nitric acid. A strong acid typically has a very low pH, often below 1 in concentrated forms. Weak acids are acids that do not fully dissociate into their ions in an aqueous solution. This means only a small fraction of the acid molecules donate protons to the solution, resulting in an equilibrium between the undissociated acid and its ions. As a result, weak acids have a higher pH compared to strong acids at the same concentration. Some common examples of weak acids are acetic acid, formic acid, and citric acid. Bases are substances that produce hydroxide ions when dissolved in water or accept hydrogen ions in reactions. They are known for their bitter taste, slippery feel, and ability to turn red litmus paper blue. Common examples of bases include sodium hydroxide and ammonia. Bases can also be classified as strong and weak bases. A base that completely dissociates in water, releasing all of its hydroxide ions, is called strong base. Some common examples of strong bases are sodium hydroxide, potassium hydroxide, and calcium hydroxide. A strong base in solution has a high pH, often close to 14. A weak base is a base that partially dissociates in water, releasing only some of its hydroxide ions. Examples of weak bases are ammonia, aluminum hydroxide, and pyridine. Weak bases often have pH ranging between 7 to 10. Salts are compounds formed when acids and bases react with each other in a neutralization reaction. This process produces water and a salt as the final products. For example, when hydrochloric acid reacts with sodium hydroxide, the salt sodium chloride is formed. Acidic salts come from strong acids and weak bases, while basic salts come from strong bases and weak acids. Neutral salts result from strong acid and strong base reactions. Oxides are compounds that contain oxygen bonded to another element, or we can say binary compounds of oxygen with other elements. Oxides are further divided into acidic, basic, amphoteric, and neutral oxides. The oxides of nonmetals are called acidic oxides. For example, carbon dioxide, which reacts with water to form carbonic acid. Basic oxides are the oxides of metals. One of the most common example is magnesium oxide. Those oxides which can act as both acidic and basic oxides are called amphoteric oxides. Aluminum oxide is example of amphoteric oxides. Neutral oxides do not react with acids or bases. Common examples of neutral oxides are water and carbon monoxide. Now let's focus on periodic table and periodicity of properties. The periodic table is a carefully organized chart that helps us understand the properties of elements and their relationships with one another. The horizontal rows in the periodic table are called periods, and vertical columns are called groups. There are total 18 groups and 7 periods in periodic table. Elements with similar chemical properties are placed in same group, and they have same outer electronics configuration. For example, member of group first A, except hydrogen, are called alkalized metals. In periods, as we move left to right, outer electronic configuration changes on each step. The periodic table is divided into 3 main categories of elements, such as metals, nonmetals, and metalloids. Metals are found on the left and center of the table, are shiny, conductive, and malleable. Examples include iron, aluminum, and copper. Nonmetals are located on the right side, are generally poor conductors of heat and electricity, and can be gases, like oxygen, or brittle solids, like sulfur. Metalloids lie between metals and nonmetals, forming a diagonal line from boron to astatine. They have properties of both metals and nonmetals, making them useful in semiconductors. The periodic table is further divided into 4 blocks based on the electron configuration of the elements, and they are S, P, D, and F block. The S block elements are those which contain their valence electrons in S orbital, such as member of group first A and second A. The members of groups third A to 8th A are called P block elements because their valence electrons lies in P orbitals. Those elements whose valence electrons are present in D orbital are called D block elements, and they are located between S and P block elements. D block elements are also known as transition elements because their properties are in transition between S&P block elements. Finally, the F block found below the main table includes the lanthanide and actinide, which are rare earth elements often used in advanced technologies. Periodicity means how properties of elements changes across groups and periods. Let's discuss the trend of ionization energy, electron affinity, and electronegativity in groups and periods. First, let's start with group trend. As we move from top to bottom, in-group atomic number goes on increasing. Extra shells are also being added, and shielding effect also increases. Due to these factors, force of attraction between nucleus and outermost electron decreases, and hence values of ionization energy, electron affinity, and electronegativity decreases from top to bottom in group. In periods, as we move left to right, although atomic number increases but no extra shells are being added, and also shielding effect remains same due to these factors, force of attraction between nucleus and outer. Most electrons increases, and hence values of ionization energy, electron affinity, and electronegativity increases from left to right in periods. Chemical bonding in inorganic chemistry explains how atoms come together to form compounds and materials. The type of bond formed between atoms determines the physical and chemical properties of the substance, such as its strength, melting point, electrical conductivity, and reactivity. There are three primary types of chemical bonds: ionic, covalent, and metallic. Ionic bonds form when one atom transfers electrons to another. This happens between atoms with a large difference in electronegativity, such as metals and nonmetals. The metal atom loses electrons, becoming a positively charged ion, while the nonmetal gains these electrons, becoming a negatively charged ion. These opposite charges attract each other, creating a strong electrostatic bond. A common example is formation of sodium chloride, where sodium donates one electron to chlorine, resulting in the formation of sodium chloride. Covalent bonds are formed when atoms share electrons to achieve stability. This type of bonding occurs between non-metal atoms with similar electronegativities. The shared electrons allow each atom to fill its outer electron shell, creating a strong bond. For instance, in a chlorine molecule, two chlorine atoms share a pair of electrons, forming a covalent bond. Another example is carbon dioxide, where carbon shares electrons with two oxygen atoms. Metallic bonds occur in metals, where atoms share a sea of free-moving electrons. In this type of bonding, the outer electrons of metal atoms become delocalized, meaning they are not tied to any specific atom. Instead, they flow freely throughout the metal structure, creating a strong bond that holds the atoms together. For example, copper's metallic bonds make it an excellent conductor of electricity, which is why it is widely used in electrical wiring. The type of chemical bond influences how a substance behaves. For instance, ionic compounds are typically hard and brittle. Covalent compounds can range from soft to hard, and metals are usually malleable and conductive. Now, let's understand some common reactions in inorganic chemistry. Let's start with combination reactions. A combination reaction, also known as a synthesis reaction, occurs when two or more substances combine to form a single product. For example, when hydrogen gas reacts with oxygen gas, they form water. Another example is when magnesium burns in the presence of oxygen to form magnesium oxide. These reactions often release energy in the form of heat or light, making them exothermic. Now let's move towards decomposition reactions. In a decomposition reaction, a single compound breaks down into two or more simpler substances. This type of reaction is the opposite of a combination reaction. Decomposition often requires an external source of energy, such as heat, light, or electricity. For example, heating calcium carbonate causes it to decompose into calcium oxide and carbon dioxide. Another example is the decomposition of water into hydrogen and oxygen gas during electrolysis. Another type of inorganic reactions is displacement reactions. These reactions occur when a more reactive element replaces a less reactive element in a compound. These reactions are simple to understand once you know the reactivity series of metals or halogens. For instance, when zinc is placed in copper sulfate solution, zinc displaces copper to form zinc sulfate and copper metal. Another example is when chlorine gas reacts with potassium bromide solution, forming potassium chloride and bromine. Displacement reactions are widely used in industries. Now, it's time to cover redox reactions. Redox reactions are chemical reactions where oxidation and reduction happen simultaneously. Oxidation refers to the loss of electrons or the gain of oxygen, while reduction refers to the gain of electrons or the loss of oxygen. For example, in the reaction between hydrogen and chlorine to form hydrogen chloride, hydrogen is oxidized because it gains oxygen, and chlorine is reduced because it gains electrons. Another common example is the rusting of iron, where iron is oxidized to form iron hydroxide. Properties of S, P, D, and F block elements. The S block includes alkali metals and alkaline earth metals. Alkali metals like sodium and potassium are soft, shiny, and have low melting points. They react vigorously with water to produce hydrogen gas and a metal hydroxide. Alkaline earth metals like magnesium and calcium are less reactive than alkali metals but still react with acids and water. Both groups form basic oxides and are essential in various applications such as sodium in table salt and calcium in bones and teeth. The P block consists of elements in groups 13 to 18. Key subgroups include the halogens and noble gases. Halogens like chlorine and iodine are highly reactive nonmetals that readily form salts when they react with metals. Noble gases, such as helium and argon, are known for their stability because they have a full outer shell of electrons. These gases are unreactive under normal conditions and find use in lighting, welding, and even in balloons. D block elements, also called transition metals, are found in the center of the periodic table. They are versatile due to their ability to form multiple oxidation states and complex ions. Examples include iron, copper, and gold. These metals are usually hard, have high melting points, and are excellent conductors of electricity. Transition metals are known for their colorful compounds, such as the deep blue of copper sulfate. The F block elements are located at the bottom of the periodic table and include the lanthanides and actinides. These elements have electrons filling the F orbital, giving them unique properties. Lanthanides, often called rare earth elements, include cerium and neodymium. They are known for their magnetic and optical properties and are used in products like magnets, lasers, and rechargeable batteries. Actinides, such as uranium and thorium, are mostly radioactive. Uranium is a critical fuel for nuclear power, while other actinides have roles in medicine and research. Despite their name, many of these elements are more common than gold in the Earth's crust. I hope this video was helpful. You can visit our channel and explore other videos on chemistry-related topics. If you like this channel, then kindly let us know which topic you want to learn and what should be the next video about. Thanks for watching. Do not forget to like and share the video.